Hey, today I'm going to review with you how to solve systems of two linear equations. And we're going to use two techniques. One is called elimination, or sometimes addition, and the other is called substitution. Let's go for it. All right, in this first system, we're going to solve it by substitution first. And when you solve by substitution, you need to pick a variable from one of the two equations and solve for it. So you could solve for x or y in the first equation or x or y in the second equation. So you have four choices. But I can see here that in row 1, my first equation, it's going to be easiest to solve for x. So if I solve that for x, I just add the 4y over. I can see that x equals -1 plus 4y. And then once you know what x is in row 1, you can substitute that x into the other equation, row 2, for x. So when you solve for one variable, you need to substitute it into the other equation. So when I do that, I get 2 times x, which is -1 plus 4y, minus 3y equals 4. And now you can see we've got one variable in this equation, and we can solve for it. So I'll distribute my 2, so we get -2 plus 8y minus 3y equals 4. 8y minus 3y is 5y. And I'll go ahead and get rid of the -2 by adding it over here. +2 plus 4 is 6. And dividing, I can see that y is 6/5. So now I know my y value. I need to figure out the x value that goes with it. And remember what it means to solve a system. Solving a system means find the x and y pair that you could plug into the first equation and make it true, and also plug into the other equation and make it true. Okay, so what I'm saying is this y value of 6/5 should work for both of these equations, or even this different version of row 1 here. So in fact, I could plug this y value into any of those three equations, and I'm going to plug it in right here and see that x equals -1 plus 4 times 6/5. And now this one's the easiest because I already have x by itself, so all I have to do is calculate this value. So -1 is -5/5, and 4 times 6/5 is 24/5. And if I add those together, I get 19/5. So x is 19/5, y is 6/5. So our solution is the ordered pair where x is 19/5 and y is 6/5. Now, just to remind you, this ordered pair is obviously something you can plot on a graph. And the reason it's an ordered pair graphically is because each of these equations represents a line. So this first equation represents a line, the second equation represents a line, and this ordered pair represents the point where those two lines are common, the point of intersection of the two lines. Now we're not doing any graphing here, but it's nice to understand what we're doing. Now let's solve this using elimination. Elimination is also sometimes called addition. And in elimination, what you want to do is somehow combine both equations together to get rid of one variable. So what I'm going to do is I'm going to multiply, let's say I want to eliminate x. Okay, we're going to eliminate x. Then I'll multiply row 1 by -2 on both sides. And now we can see that if I rewrite my row 1, I get -2x plus 8y equals +2. And let's just copy row 2 underneath that, 2x minus 3y equals 4. Well, I can see now, if I add my two rows together, then the x column, the x terms will cancel. So that's also why it's called addition sometimes. So I'll add the two equations together. And it's also very important that you set both equations up in the same format. So this is often called standard form, where you've got your x term plus your y term equals your constant, so that everything lines up here. So when we add these together, the x's eliminate. I get 5y equals 6, and I can see that y equals 6/5, which is the same y value we got solving this via substitution. Now I can plug this y value back into any equation with x and y. So let's plug it into the first equation, x minus 4y, so x minus 4 times 6/5 equals -1. And if we solve that for x, we get the same thing we did before, 19/5. So we still get the same ordered pair solution that we did before in a slightly different way. Let's do one more example in both ways. Now in this example, let's talk about which choice might be easier or more natural choice for solving, either elimination or substitution. And in this case, if we were to try substitution, let's say we wanted to get this y by itself. I would eventually have to divide by this coefficient of 3, which would result in fractions when I solve for y. And in fact, all 4 variables exhibit that same problem, that if I were to solve for x, y, or x, then I'd have to divide and get fractions. Now, there's nothing wrong with fractions. We can certainly do it. In fact, we're going to solve this by substitution, but let's solve it by elimination first, because that might be the more natural choice. Now, I have to decide if I want to eliminate my y's or my x's. And so let's say I want to eliminate the y's here. Then I have to turn my coefficients 3 and 2 into the same coefficient with opposite signs. And we do this by multiplying each equation on both sides by a number. And so the question becomes, what can I turn a 3 and a 2 into via multiplication? And the answer is like 6 or 12 or 18, any common multiple of 2 and 3. So what I'm going to do is turn one of these into +6 and the other one into -6. So let me multiply row 1 by -2 and row 2 by +3. And when we do that, we get -6y plus 4x equals 2. And then we get +6y plus 9x equals 63. And we can see now that the y's will cancel when we add the 2 rows together. So we get 13x equals 65. And dividing by 13, we can see that x equals 5. There we go. Now that we know x, we can plug that back into either of the 2 equations we started with to solve for y. So I'm going to plug it into the second row. So I've got 2 times y plus 3 times x, which is 5, equals 21. So 2y equals 6, which means that y equals 3. So our solution is the ordered pair 5, 3, which is the point where these 2 lines intersect. Let's try this one again using substitution. So now we have to pick y or x from one of the 2 equations. I'm going to choose the y in row 2 because it has a smaller coefficient of 2 and it's also positive, so I don't have to deal with a negative like I would if I solved for x in row 1. But you can do this with any of the 4 variables and you should get the same answer. So if I solve that for y, I'm going to subtract my 3x over and divide both sides by 2. So y is 21/2 minus 3/2 x. And now that I know y from row 2, I have to substitute that in for y in row 1. So I've got 3 times 21/2 minus 3/2 x minus 2x equals -1. And now I need to solve this equation for x because that's the only variable remaining. So we get 63/2 minus 9/2 x minus 2x equals -1. And you can see the fractions floating around here. You can work with them as they are. I'm not using a calculator here, so I'm just going to get rid of all my fractions by multiplying both sides by 2 at this point. So I get 63 minus 9x minus 4x equals negative 2. And that looks better. Negative 9x minus 4x is negative 13x. I'm going to subtract 63 over to get negative 65. And when I divide by negative 13, I can see that x is 5, which is what we found before. And again, I can plug that x value back into any of the original two equations or this guy right here, which is better for us because that gives us y directly. So y equals 21 halves minus 3 halves times 5. So we have 21 halves minus 6 halves, or sorry, minus 10 halves. Sorry, minus 15 halves. There we go. I'm ahead of myself. So that's 6 halves, which reduces to 3. And so our solution again is the order pair 5, 3. And that's a quick review of solving systems of two linear equations by substitution or elimination.